Welcome back to a Regents physics review. This is for electricity. These are multiple choice questions from the June 2022 exam. So let's move in to our first example. All right, so example number 1. The direction of the electric field at a point in space is defined as the direction of the force exerted by the field on A. Alright, so this is a big idea in electric field. We even did a lab simulation on this where you were given what is called the point charge with either positive or negative, and you had those little red dots that were test charges, and you saw how they reacted when you had a negative charge in the middle or a positive charge in the middle. So what I'll do here is make my two charges, so I'll have a negative here, and I'll have a positive over here. So what I'm going to do with this, I'm not going to draw the field lines between them. I'm just going to draw the field lines for each of these charges, so act like they're in their like own little box here. So for the negative, when you have the negative, it goes into the negative. So when you have your field lines, it looks like something like this. Right, just roughly, that's like not perfect field lines, but roughly it goes into the negative. When you have the positive, it goes away. So what this is essentially showing is a positive test charge. Because you see with the positive charge here on the right, the lines point away. This is showing that if you had a positive charge that came near it, it would be repelled because obviously when you have like charges, they repel. This is the same thing for magnets, like poles and the magnets, they repel. Same idea here for my negative charge. I'll write that a little bit nicer. Same idea here for the negative charge. The arrows go into the negative charge. So that is showing that whatever the charge you use to create these field lines is being attracted to it. So the positive test charge, that would then be attracted to the negative point charge as you have the lines moving in. So essentially, all you're looking at this is a positive test charge located at that point. Again, you have the positive here on the right. This shows that if I put that positive test charge near it, it would be repelling. You have the negative test charge, not negative test charge, negative point charge on the left. The arrows show that this test charge, this positive charge, would then be attracted to it. So answer choice 4, a positive test charge located at this point. That's what makes my electric field lines. All right, so moving on to our next example. Example number 2, with a 1 kilometer length of copper wire A with a cross-sectional area of 1.0 times 10 to the negative 4th meters squared, has a resistance of 0.172 ohm at 20 degrees Celsius. Another copper wire B is half as long and has twice the cross-sectional area of wire A. What is the resistance of copper wire B at 20 degrees? So there's two ways to go about this question. You could either do a law of ones, or you could actually just plug in what they give you based on the changes in the values for copper wire B. I'm going to plug in because it's probably easier to visualize what's happening with that versus a law of ones where you just plug it in one or double it or half it based on what they're telling you. Here you can get a concrete answer and you can feel a little bit better about what you've done. So let's look at wire B here. The first thing that's going to stand out to me is it is another copper wire. So whenever you have a material, and it even says here at the bottom at 20 degrees Celsius, that 20 degrees Celsius is only going to be one place on the Regents reference table. And it's going to be in the electricity, on the page for electricity. Towards the bottom, you have their resistivities at 20 degrees Celsius. So whenever this happens, whenever you're given 20 degrees Celsius and some material, this should tip you off to using the resistivity table. On this one, we have copper. It gives me the value for copper here. So resistivity, again, if you don't know what the the variable used for resistivity is going to be. It's on the right side of the reference table. You look for resistivity there. It looks like P. It's called the Greek letter rho, but you can call it like a little p if you so choose. So you have there the Greek letter rho, my resistivity. Again, it is another copper wire. So I go to the resistivity table. I find out what copper is, and it tells me it is 1.72 times 10 to the negative 8th. So 1.72 times 10 to the negative 8th. And if I don't know my units for this, though it's not as important for a multiple choice question, if I don't know my units for this, it is on the table here as well. Resistivity is ohms times meters. So if it comes up on a part 2 question where you have to show all work, you can get the units straight from there. So you have ohms times meters. All right, so we have resistivity. It then tells me that this wire is half as long as the original wire. So it tells me the original wire is 1.0 kilometers. So we're going to have to convert that into meters. So the original wire's length here, L, is 1.0 kilometers. So that should actually give me half a kilometer if we're dividing it by 2. So we should have 0.5 kilometers for this new wire. If we're going to convert this into meters, we know that for 1 kilometer, it's 1,000 meters. So what we can do with this, and that also comes from the reference table. If you look for what kilo is on the reference table, it's 10 to the third. So that's essentially telling us again that 1 kilometer is 10 to the third meters. So we can do this real quick. 1 kilometer, 1 kilometer is going to be equal to 1,000 meters. All right, so if we then get this, do the quick conversion, 0.5 times 1,000, my kilometers is going to end up canceling out because you have kilometers on top, kilometers on the bottom. 0.5 times 1,000 should give me 500 meters. All right, what else do we have here? We have that has twice the cross-sectional area. Originally, it gives me a cross-sectional area of 1.0 times 10 to the negative 4th meter. So just multiply that by 2, and you will end up with your new cross-sectional area, which should be 2.0 times 10 to the negative 4th. So our new cross-sectional area, we're just doubling this. So this is A on the reference table. Again, that's on the right side. If you forget that, at the very top of electricity. This one is going to be 2.00 times 10 to the negative 4th, or you can just put 2 times 10 to the negative 4th, and that is going to be meters squared. The other thing that we should have here, we are looking for resistance because it's asking us to find the resistance of the wire at 20 degrees Celsius. So R equals question mark. So now look at your reference table, look for an equation that involves all of these variables. We have resistance, that's what we're looking for, area, the length, and my resistivity. I see an equation towards the bottom. There's only 2 of them that involve resistance directly besides my series and parallel circuit rules. I have either R equals V over I or R equals rho times length over cross-sectional area. If you look at this, this is the correct equation here. R equals rho times length over cross-sectional area. So we have here looking for resistance. And this is our equation. So now let's go plug everything in and end up with our answer. So we want the resistance R. Plug in all my numbers in. It's good practice to plug in with units. for later on the free response questions. So my resistivity rho is 1.72 times 10 to the negative 8th ohms times meters. This is then multiplied by my length of the wire, that is 500 meters, all over my cross-sectional area, which is 2 times 10 to the negative 4th meters squared. So I'll do this first is just quickly multiply the top. So just get all the steps in, just in case anybody is a little bit confused. So we have 1.72 times 10 to the negative 8th. That is times 500. So the top should now end up being 8.6 times 10 to the negative 6th. And my units should then end up being ohms times meters squared, all over my cross-sectional area, which is 2 times 10 to the negative 4th, and that is meters squared as well now. So you should see that units are going to cancel and give me my ohms, which is my unit for resistance. So now I'm just going to plug this into the calculator and end up with my answer. So 8.6 times 10 to the negative 6th, 2 times 10 to the negative 4th. Doing the quick division here, I should end up with my answer as 0.043 ohms. So my resistance is 0.043 ohms, which is answer choice 1. So again, with the units here, you have meters squared on top, meters squared on the bottom. So that will end up canceling, and you're left with ohms, which is going to be my unit for resistance. So we know based on our units, we got the correct units, and then just plugging everything in, we have our answer here. Answer choice 1, 0.043 ohms. So let's move into our next example. All right, so example number 3, we have the magnitude of electric force exerted on a small positive charge located between two oppositely charged plates is smallest near the positive plate, smallest near the negative plate, greatest midway between the plates, and the same everywhere between the plates. So the first thing with this question is, what are two oppositely charged parallel plates? So with this, it kind of works like an electric field. You have two oppositely charged plates instead of 2 point charges. So my first one I can make here, they look like so. The first one I can make here, let's say this is going to be all positive. The second one that is parallel from it would then be all negative because they are oppositely charged. They follow the same exact rules. The electric field lines go out of the positive and into the negative. So now we can visualize this. We can actually use an equation and just a concept in order to get this answer. So the main concept behind all of this is that my electric field strength is the same throughout the entire plate. And this is actually going to drive what happens to my electric force. So there is an equation on the reference table that can show this, and it is the only equation that involves electric field strength. So if you don't know what the variable is for electric field strength, you look on the right side of the reference table, you look for E, which is, or you look for electric field strength first, and then you see that is equal to E. So I have here E is equal to, and this equation does involve Fe. So you have that E is Fe over Q. So it's the electrostatic force over my charge. So since we know that, well, what our charge is here, it's positive, it's not going to change for this situation. And we know that the electric field strength, just based on concepts, is the same throughout the entire plate. We can kind of look at the equation then, no matter what I'm going to do, just doing a little bit of algebra, E times the charge equals Fe. If we know what our charge is, which it's a positive charge, it's some number, that's not going to change unless we change the actual particle. And then no matter where I go in the entire between these two plates, my electric field strength is not going to change. So that means then my force is not going to change. So there's nothing I can do by moving it between these plates to change this, because I know what Q is. If they gave me some number, I would have that. And then E, no matter where I move between these two plates, that's not going to change. So any part that I put this, the combination of E and Q is always going to be equal to the same force for any situations, no matter like what type of charge it is. If I have that value Q, if I have the value of E, no matter where I move it between these two plates, that combination, multiplying them together, is always going to equal whatever that electric force is going to be for that situation. So it's the same everywhere between the plates. Answer choice 4. So again, this is driven by my electric field strength being the same throughout the system no matter where I move it. That doesn't change. I know my charge. Multiplying those two gives me whatever number the force is going to be. So that's the same between both plates. So let's move into my next example. So example number 4. Compared to the resistance of an aluminum wire at 20 degrees Celsius, the resistance of a tungsten wire of the same length and diameter is approximately, is at 20 degrees Celsius as well. So let's look at what they give us in the question and kind of figure out what equation we're going to be using to compare to one another. So the first thing that jumps out to me here is that I have my resistance, or it's saying compared to the resistance. So if I look at the reference table, resistance again, I look for resistance that is going to be R. So we put R in here. Next thing, I'm given that I have an aluminum wire at 20 degrees Celsius. Again, on the reference table, 20 degrees Celsius only comes up once, and I'm on the page that is on. If you look at the bottom of the page, it says resistivities at 20 degrees Celsius. So what I have here then is my resistivity of the aluminum wire. They give it to me as the first one actually on the table. So resistivity, again, I look on the right side of electricity. I look for resistivity. Next to it is equal to this letter. It looks like a P is the Greek letter rho. The other thing that they give me next, they give me a little more information here, is a resistance of a tungsten wire of same length. The length, that's on the reference table as well, that is just L. And then the final thing is diameter. Diameter is not directly on this portion of the reference table, but there is something in here that can like directly correlate to diameter. And if you look at the very top area, if you think of a wire, it is going to be a circle. Diameter is going to give me the area of the wire if I do the proper math. So area is also going to be involved here in the comparison. So what equation involves resistance, resistivity, length, and area? There are two that have resistance is equal to on the reference table, but there's only one that involves all of these variables. So we have here R equals rho times L over A. So what we can do with this is find our resistivities, and we're pretty much comparing the resistivities to each other because nothing else changes. It says that they have the same length and they have the same area because they have the same diameter. So we can plug in for the length and the area 1, and for the resistivities, we can get a little practice at looking for resistivities and plug those in and then compare them to each other. So the first one here, we have my aluminum wire. So I'm looking for my resistance. That is equal to the resistivity of the aluminum wire. And this is going to be 2.82 times 10 to the negative 8th. And that unit is ohms times meters. That is given to us on the reference table. Since we're not given actual values for length and diameter, but they say they're the same, we can just plug in 1 for both situations. So we're going to say the length is 1 meter, and we're going to then also say that the area is 1 meter squared. So if you do the quick math on this, it's just 2.82 times 10 to the negative 8th times 1 over 1. So the resistance for the aluminum wire is just 2.82 times 10 to the negative 8th ohms. You could have also done this with just a regular law of ones and just kind of compared the two resistivities to each other from the beginning, but this kind of like makes it a little bit more clear. For the tungsten wire now, we're going to do the same exact thing. Just plug in to the equation. So R equals what's going to be my resistivity. My resistivity for the tungsten wire is going to be 5.6 times 10 to the negative 8th ohms times meters. Again, since they tell us that the length of the wire and the diameter is the same, we can just plug in 1 for each of these, so my calculation is the easiest. So my length can be 1 meter, and my area can be 1 meter squared. Again, easy calculation here. You end up with the resistance as then 5.6 times 10 to the negative 8th, and we'll have ohms because the meters squared would then cancel out on the top and the bottom. So now just comparing these two to each other, we're comparing the resistance of the tungsten wire to the resistance of the aluminum wire. Our tungsten is down here, so this is the tungsten wire. This one up here is my aluminum. So my aluminum is up top, my tungsten is on the bottom. We're just comparing these two to each other. So essentially divide 5.6 times 10 to the negative 8th by 2.82 times 10 to the negative 8th, and you will end up with your answer. So 5.6 times 10 to the negative 8th. And they have the same exact scientific notation, so you can really just divide the two numbers here as well if you want to go a little bit quicker. Divided by 2.82 times 10 to the negative 8th. And you end up with 1.99, so approximately 2 times more for the tungsten wire compared to the aluminum wire. So this is going to be twice as great for my resistance. So let's move in to our next example. All right, so example number 5. How much energy is expended when a current of 5 amperes is in a 5 ohm resistor for 5 seconds? So the first thing here, this is just going to be a pick out what I have from the question and then use an equation based on that situation. So the first thing here, I have how much energy. What is energy for electricity? If I look on the right side of the reference table, I look for electrical energy. It tells me that this is work. So work, W, and it says how much of this. So this is the thing that I'm looking for. That's my question mark. Next thing I have here is that I have a current of 5.00 amperes. Again, if I don't know what current is at this point, I look on the right side of the reference table and I find that current is I. So I is then going to be equal to 5.0 amperes, or just 5 amperes. Then it says this is in a 5 ohm resistor. So again, resistor, that has to do with resistance. If we don't know what resistance is, that is going to be R. And we have here 5 ohms. Then the last thing here is for 5 seconds. That's going to be my time. And that is going to be 5 seconds. So essentially with this, I just want to look for an equation that involves work, current, resistance, and time. I should really then be looking at my work equations on the very bottom here above series circuits. I'm going to find here that W equals, so that's what I'm looking for. So W equals. I have here my current, resistance, and time. So I look for an equation with this, the third one in line of all the work equations. I see that I have I squared times R times T, and that is the equation I am going to end up using. So I squared times R times T is going to be my equation. So now you just gotta plug in what you have here. So work is equal to my current is 5 amperes squared. My resistance is 5 ohms. And then my time is 5 seconds. So just quickly here, 5 raised to the second power, that's going to give me 25 amperes squared. Multiplying those two together, I'm going to have then 25 ohms times seconds. And then just multiplying 25 times 25 together, that's going to give me the unit of joules. 25 times 25, you may have memorized this from math class. So 25 times 25 is going to give me 625 joules. And that is going to be my answer. Answer choice 3, 625 joules. So let's move on to our next example. So example number 6. The amount of electrical current through an unknown resistor may be measured by connecting. So we have 4 different choices here. We have 1, an ammeter in series with the resistor, 2, an ammeter in parallel with the resistor, 3, a voltmeter in series with the resistor, and then 4, a voltmeter in parallel with the resistor. So current is amperes. So if you're looking at like what kind of works with amperes here, you have the ammeter and the voltmeter. Meter just means I'm measuring either current or voltage or potential difference. So think about like meter is a measurement of distance when we do it in kinematics. So meter is measuring something. It's not actually giving me either of these things. It's just measuring the current or the voltage potential difference in the circuit. So the one that goes with potential difference or voltage should be clear because that is voltmeter. So 2 answer choices I can get rid of right away are answer choice 3 and 4 because they're not going to measure my current. They're going to measure my potential difference or voltage. So those 2 can go away right away. Then you have 1 and 2. So 1 is that the ammeter is in series with the resistor. So if I'm going to make a quick little diagram of this, say I have my battery, and I have my resistor somewhere. In series means that is in the same pathway as the resistor. So if I look at the reference table, a ammeter is A like that. So that would be in series with the resistor. If it was in parallel with the resistor, and I made my diagram again, you'd have something like this. You have something like that. So what happens if you had an ammeter in parallel? And I think I showed this when we did those circuit labs with the FET lab simulations. If you have the ammeter in parallel with the resistor, what is going to happen is with the ammeter, that is going to have no resistance essentially. So if you have that happen, the circuit will set on fire. So you can't have it in parallel because it's just going to take the path of least resistance, the current, and then there's going to be no resistance in the circuit. The current's going to run too fast, and you're going to set the circuit on fire. So you need the ammeter to be in series with the resistor because the resistor gives you the resistance in the circuit, and the current has to then flow through that resistor so it slows down the current. Otherwise, again, if you had a situation like this, you'd end up with the um, circuit set on fire. So this one is no good. This is what you want. You want the N meter in series with the resistor, because then the current is forced to go through the resistor. So you end up getting the proper current reading, and the circuit doesn't set on fire. So answer choice A, series circuit. So don't try that with a real circuit. If you want to see that, go to a FET simulation and set up a N meter in series with the resistor. So make something like this. The FET simulation actually shows like the battery very much the same. These diagrams, based on the circuit diagrams you have in the reference table, they're very much the same diagrams in the FET simulation. So you can actually test an N meter in series versus an N meter in parallel and see what happens to the circuit when the N meter is in parallel. You get an extremely high current, and the circuit sets on fire. So again, don't try that at home with a real circuit, please, because you'll blow up whatever it is that you're going to use to measure the current. Try it, but if you're going to try it in a FET simulation, and I can actually link that in the description below as well. So let's move into our next example. All right, so example number 7. We have two charged spheres are located distance d from each other and experience an electrostatic force attraction Fe. If the magnitude of the charge of each sphere is tripled and Fe is unchanged, what other change must have occurred? So this is going to be a law of ones question again. So we've done this at universal gravitation. Coulomb's law is going to be universal gravitation's cousin, essentially. Very similar equation, but just different variables, and it's for electrostatic force and not gravitational force. So where did I get Coulomb's law from? So I have two charged spheres. So what is a charge? A charge is Q on the reference table, and it tells me I have two of them. So essentially I have Q1 and I have Q2. It then tells me they're located a distance d from each other. The distance on the reference table is going to be given to me as just r squared, or just r on there. So we have here my distance between the two is going to be r. And then we have Fe, that is the electrostatic force. So, and with this, there's also then a constant K, but we're not too worried about that at the moment, because that is going to be always unchanged. So this gives us the equation here, Fe equals K Q1 Q2 all over r squared. We can plug in d instead because that's what they're giving us. But we're just looking at the difference between these. So it's telling me that the magnitude of the charge on each sphere is tripled, but Fe doesn't change. So let's get a baseline of Fe first by doing the law of ones. So we'll get essentially 1 for the force of electricity, and then we're going to have to figure out what other thing is going to change to give me no change. So I want to get here that Fe is 1. My constant K, we plug in as 1. My charges are 1 and 1. And then my distance is also going to be 1 then squared. So this is essentially our baseline for the law of ones. This is what we're going to compare to when they tell us about the changes that are going to occur. So we do all of this. This then gives me 1 Fe, because you have 1 times 1 times 1 over 1. Simple calculation for that. That'll give us our baseline. Now we're going to put in our changes. So our changes here. It says that the charge on each sphere is tripled, yet Fe is unchanged. So we should still get 1 Fe. K is always going to stay the same because it is a constant, so we just plug it in as 1. We don't need to plug in the entire constant and like have a bunch of variables or units and stuff like that. It's not useful in this situation. Just plug in 1 for it. Makes our calculation a lot easier. And it says that the charge in each sphere is tripled, so we can put in 3 for Q1 and Q2. So then we're figuring out what is going to happen here. What else is not going to then change to give me 1 FE essentially on the other side. So 1 on the other side. What I'm going to do with this is solve for R because R is the only other thing that can end up changing. And it says here 1 and 2 are the signs, but it's saying that FE stays the same, so that doesn't really matter in a situation. It's not telling us like that they are now all of a sudden repulsive, so the signs are not going to change. So 1 and 2 doesn't really matter. So I'm going to do here is solve for R squared before I'll do the math real quick. So it should be 1 FE is equal to 9 over R squared. So we have to be able to solve for R here. So I'm going to have to move this over here. So 1 FE is equal to 9 over R squared. So quickly doing this, I just want to solve for R. So I have 1 on the other side. I want to get R by itself. So let's do R squared on both sides of the equation. I have here R squared is equal to 9 over essentially just 1 in the situation. I'll need to put in the FE as well. So if I want to now solve for R, I want to get R by itself, take the square root of it because it's being squared. So the square root of R squared and essentially the square root of 9 on this side. We have here that R is going to be equal to 3 because it shouldn't be plus or minus 3 in the situation because we're looking at distance. And we have a negative distance. We have a negative displacement, but we don't have a negative distance. So just put it as R is going to be now 3 times the original. That's what that is saying because we had an original of 1. So now R is 3. So I've tripled it or increased it by a factor of 3. That is going to be answer choice 3. So again, that should make a little bit of sense. If I plug this back in, 3 times 3 over 3 squared, that should give me 9 over 9, which then should not change the force of electricity. So increasing the distance, or R, by a factor of 3 gives me no change in the force of electricity. So let's move into our next example. All right, so example number 8. We have several resistors are connected in series in an electrical circuit. The potential difference across each resistor. So we have here varies directly with the resistance of each resistor, varies inversely with the resistance of each resistor, varies inversely with the square of the resistance of each resistor, or is independent of the resistance of each resistor. So think about our rules for voltage and current and resistance in a series circuit. So the first thing here, my current is the first thing that comes up in series circuits. It is basically saying that my total current is equal to my current at each of my resistors. So we need this to hold true when this occurs. So this also then leads us to our rule for voltage, and our rule for voltage is going to be that the total voltage is equal to the voltage at resistor 1 plus the voltage at resistor 2, and then etc. And then for my total resistance, or my equivalent resistance, it's just adding up all the resistors together. So let's say my equivalent resistance Req is equal to R1 plus R2, and then etc. So what's the equation that kind of brings all of these together? My resistance, my potential difference, and my current. There's only one of them on the reference table that involves like all 3 of these, and it helps us relate them all together, and it is R equals V over I. So we need our current to be the same throughout the entire circuit. So essentially, in order for this to occur, we must have that our resistance and our potential difference have to vary directly. So we do a little bit of algebra here, moving my I to the other side by itself. So you have IR is equal to V, then dividing out R from both sides, I equals V over R. So my current has to be the same throughout the entire circuit. Say we know what the battery is, we know what these resistors are. My current has to be the same throughout the entire circuit. So in order to have this to hold true, if my resistance goes up at one of these resistors, if I come across a bigger resistor compared to the resistor I went across before, my voltage also has to actually go up in order to allow my current to remain the same in the entire circuit. It would be the same idea if my resistance went down, my voltage also has to go down. It might be a little bit clearer with R equals V over I, because if I is the same, I have R and I have V, you can see that they vary directly. So if I have V going up, I have to have R going up. If I know what the current is going to be. And this is all again driven by this current being the same throughout the entire circuit. This is again not getting my equivalent resistance or not changing the voltage and then saying that my resistance is going to change. That's not the case. It's saying that I know what my current is, so it's kind of like the same idea. I know what my current is, so I have to then figure out that if my voltage goes up, my resistance also goes up in order to make sure that my current is equal throughout the entire circuit. It's kind of the same, a little bit of the same idea as that Ohm's Law lab, where if I increased my voltage, my current also had to then increase because my resistance was the same. I didn't change my resistors. Just looking at now, my current is the same. I'm not changing my current, and my voltage across, this is again across an individual resistor. So the resistors are different. So if my voltage goes up, my resistance goes up. That is varies directly. So answer choice 1. This varies directly with the resistance of each resistor. So let's move into my next example. That's example number 9. We have the diagram below shows the initial charge and position of two identical conducting spheres on insulating stands. If the spheres are brought into contact with each other and separated, sphere B will have a net charge of. So the idea with this is whenever I have two charged objects that come in contact with each other, the charge wants to spread as evenly as possible. This is what we call conservation of charge. And essentially what happens is the charge on each of these two conducting spheres will be the same after they come in contact with each other. So all you do with this is add these two numbers together and then divide by 2 afterwards, because then you get the total charge in the system. You want the charge to be the same on each of these spheres. You only have 2 of them, so you divide by 2. So just add up my charges. So essentially, Q initial has to equal Q final in the system. And it wants to be spread as evenly as possible. So my charge here is going to be -7 times 10 to the -6 coulombs, plus 3 times 10 to the -6 coulombs. So if I add these two together, they have the same exact scientific notation, so we don't have to worry about that really. It's really just -7 plus 3. That's going to give me -4 times 10 to the -6 coulombs. And again with this, I want the charge to spread as evenly as possible. So since I have 2 of these conducting spheres, I divide this number by 2, and I get the charge on each of the spheres. So divide by 2, -4 over 2 essentially is then going to give me -2 times 10 to the -6 coulombs, which is going to be answer choice 2. So again, the idea behind this conservation of charge, my charge has to spread as evenly as possible, or it wants to spread as evenly as possible at all times. So when they come in contact with each other, those charges transfer between the two spheres and give me an equal amount on both for the total charge. Since my total charge is -4 times 10 to the -6 coulombs, I divide that by 2 and end up with -2 times 10 to the -6 coulombs. Our answer choice is answer choice 2. So let's move into our next example. So example number 10. We have what is the current in a conductor if 3.15 times 10 to the 18th electrons pass a given point in the conductor in 10 seconds. So again, this is going to be a math question, so let's pick out what they give me in the question and then use a certain equation based on that to get the answer. So my first thing here is what is the current? So again, current, if I don't know it by this point, I look at the reference table, I look for current on the right side of the reference table, and I see that current is equal to I, and it's asking me for what this is, so that is going to be my question mark because it doesn't give me a value for the current. And then it tells me that 3.15 times 10 to the 18th electrons pass a given point. This is also actually a charge, but it is not in coulombs, it is in elementary charges. This is the dreaded having to convert into coulombs. For some people, this could be a little bit more difficult. For some, this comes really easy. I will explain it again how this happens. So we have here that it is a charge actually, and it is 3.15 times 10 to the 18th, and it is going to be elementary charges. And it then tells me that they pass over the 10 seconds, so time is 10 seconds. So on the reference table, we have an equation that involves all of this. We have current is equal to the change in charge over time. So we have here I is equal to the change in charge over that time interval. So the main thing we have to do here is convert my elementary charges into coulombs, because otherwise this will not be the correct answer. So how am I going to end up doing that? So on the reference table, it tells me that one elementary charge is going to be 1.6 times 10 to the negative 19th coulombs. That is the easiest way of conversion. I also have elementary charges as well is 1 coulomb, so I could do that one, but that's a little bit more of a pain. But it will all work out the same, whichever one you do. You just want to get rid of elementary charges. So elementary charges has to go on the bottom because you want to divide out the elementary charges. I'm going to use the one that says 1 elementary charge because that is just a little bit more comfortable for me. So I have here elementary charges on top, elementary charges on the bottom, so these will end up canceling. And then I put what my elementary charge is in coulombs at the top here, so I end up with my unit as coulombs. So I have here that 1 elementary charge is 1.6 times 10 to the negative 19th coulombs. So now let's plug this into your calculator. 3.15 times 10 to the 18th times 1.6 times 10 to the negative 19th coulombs. So 3.15 e to the 18th, or times 10 to the 18th is the e function in the calculator, or the double e function in the calculator. You have this times my charge in coulombs, so 1.6 times 10 to the negative 19th. This is going to give me a charge here of 0.504. And this is now going to be in coulombs. If you were to use that 1 coulomb is this many elementary charges, it may have actually worked out a little bit better because you would have put in 6.25 times 10 to the 18th, and the 18th would have 10 to the 18th would have canceled out easily, so it would have been left with 3.15 over 6.25. Because for coulombs, you would have plugged in 1 coulomb, and you would have plugged in on the bottom the 6.25 times 10 to the 18th elementary charges. That would have also given you the same exact charge as 0.504 coulombs. But this is the more common way to convert into coulombs. This is why I did it that way. So I'm just going to plug into the equation because I have my charge in coulombs and I have my time in seconds. So current is equal to the change in charge, is essentially just the charge in this situation. So 0.504 coulombs is going to be over 10 seconds. So then just plug this into the calculator. 0.504 divided by 10 is going to give me my current is equal to 0.05, and it just goes to 50 in the answer choices, so we'll just do 50 here as well, and that is going to be amperes. So that is going to be answer choice 1, 0.050 amperes. So let's move into our last example. So example number 11, we have a particle with a charge of 3 nanocoulombs. It is placed in an electric field with a magnitude of 1500 newtons per coulomb. What is the magnitude of the electrostatic force exerted on the particle by the electric field? So let's look again. This is just a plug-in question, so let's look at what we have in the question, then figure out what equation we are going to use based on that. So you have a particle with a charge of 3 nanocoulombs. So again, we have a charge here that is going to be Q on the reference table. It gives us to us in a different style of unit. That is not the same prefix we are used to for coulombs, but we will convert, and I'll show you how to. So we have here 3. Then what is nano? Nano is just N. And coulombs is C. We'll convert that in a second. Then we are given that is placed in an electric field. And this electric field has a magnitude of 1500 newtons per coulomb. So again, the reference table, electric field strength is big E. And they give it to us as 1500 newtons per coulomb. Then the last thing here is saying what is the magnitude of the electrostatic force exerted on the particle by the electric field. So that is going to be Fe, and that is a question mark. So the first thing I want to do here before I do any equation, any math, I want to convert from nanocoulombs into coulombs, because otherwise I'm going to not get the correct answer. So how are we going to actually do that? So that's not like a common conversion that we've done, that we usually do. So let's look at the reference table and look for what nano is, because that's essentially going to tell us how many coulombs are in a nanocoulomb. So we're going to put on the bottom here 1 nanocoulomb. And based on the prefix for nano, that is going to tell us that how many coulombs are in 1 nanocoulomb. It says there on the reference table, nano is 10 to the negative 9th. So essentially, 1 times 10 to the negative 9th coulombs are in 1 nanocoulomb. So that means that when we do the conversion, nanocoulombs will cancel out. I do 3 times 1 times 10 to the negative 9th coulombs, and that is going to give us 3 times 10 to the negative 9th, negative 19th, that is not correct, negative 9th coulombs. And that is going to be our conversion. So now we can look for our equation and end up with our answer. So we're looking for the electrostatic force, and we have the electric field strength and the the charge of the particle. So this equation is going to be E equals Fe over Q. That is the only equation that involves all 3 of these variables. So electric field strength is equal to the electrostatic force over the charge. And what I'd like to do with this first is just solve for Fe, because it's good practice for the part 2s, and then plug in. So to get Fe by itself is currently being divided by the charge Q. That is, the opposite of that is going to be multiplication on both sides of the equation. So we multiply Q on both sides. So electric field strength times the charge. I'll just put that in parentheses actually. electric field strength times the charge Q is then equal to my electrostatic force. So now we're just going to plug into the equation and we're going to end up with our answer. So electric field strength here is 1500 newtons per coulomb. That is then going to be multiplied by our converted from nanocoulombs into coulombs. That is 3 times 10 to the negative ninth coulombs. That is then equal to my electrostatic force. So now just multiplying these two together, I have 1500 newtons per coulomb times 3 times 10 to the negative ninth coulombs. So plug this into your calculator and you will end up with your answer. And you're going to end up with 4.5 times 10 to the negative sixth. And you should have your units now as newtons because it is a force, and the coulombs end up canceling out because you have coulombs on top, coulombs on the bottom. That is going to be equal to my electrostatic force, Fe. So that is going to be answer choice 1, 4.5 times 10 to the negative 6 newtons. Alright, so this is our last example. So I hope this video was helpful. I also put out a free response video as well for electricity. That should be out within the next few days. And see you guys in class, and good luck studying for the Regents.